Thank you for the invitation and the opportunity to be here. And today I'll be talking about some joint work that I've done with Arpita Ghosh, who's at Cornell, Aaron Roth at Penn, and Grant SchoenebeckWe, who's at Michigan. And the motivating story is one that's, I think, quite familiar to all of us, is that individuals have lots of really interesting information, and we're interested in computing on that information or aggregating it in some way. And the focus in most of my talk today will be on simple forms of aggregation, very simple computations we might want to do in individuals' information, and towards the end I'll try to hint at what we might do in terms of more sophisticated computations. But let's first just talk about aggregation of individually held information and some of the challenges and techniques that we've seen there so far. So one example of sort of a class of techniques that have received a lot of attention in recent years is prediction markets. So the basic idea there, if you're not familiar with them, is that prediction markets are a setup that allow individuals to bet on outcomes of a future observable event. So basically an individual can just say, I think so-and-so is going to be elected the next US president, and they will be compensated for predicting well, basically for moving the market in the right direction. There's been a lot of nice work here in terms of theory, and they've gotten some good publicity over the past elections and other events that people have tried to predict in terms of their ability to do so. They've also actually gotten a lot of attention within corporations, at least in the US. I'm not sure about in other places. There are lots of companies that try to use internal prediction markets to aggregate the wisdom of the crowds. So the employees of a company might actually have a much better sense than a few higher ups in the company about whether an important product is going to launch on time, and the company would like to aggregate that information. They don't particularly care what you think or what you think. They want to know the collective wisdom, and they somehow want to incentivize you to provide that collective wisdom. So that's also been used. And it seems companies think that the wisdom they've been gathering is useful there. Of course, prediction markets have also run into some pretty public problems in recent years. This isn't the focus of the talk, but just to acknowledge that as with any technology, there are downsides. So we've seen evidence of attempted manipulation of prediction markets, and there have also been some interesting sort of regulatory and legal issues that have come up in this context, such as being banned by the US CFTC. There's this question of what are prediction markets? Are they betting? Is it options trading? Who should be regulating it? There have also been some financial difficulties involving prediction markets shutting their doors. There have been some awkward political situations that have caused prediction markets to shut down. You may remember some of these stories from recent years. But stepping back from some of the practical problems that they've encountered, there are some theoretical challenges of prediction markets in terms of what they can actually show that they're aggregating. But I want to focus on some different challenges, some problems that prediction markets really even formally aren't addressing. And the basic problem is, well, what if we're interested in aggregating privately held information in situations where there's no publicly observed outcome? So it's not a situation where there is going to be an election on a particular day in November. We're going to find out who's elected, and therefore we can compensate people for predicting this well. But rather, we'd like to aggregate beliefs in situations where there's no ground truth that we'll later be able to refer to. So maybe we want to know, do our employees think we should acquire a particular other company? Not really a ground truth to judge based on, but there may be some aggregate wisdom. How can we incentivize people to share their wisdom and make sure they're giving us what they really believe? What's the prevalence of drug use or other bad behavior in our company? Do our employees accept bribes or students cheating in class? You may have some beliefs about these things, but there's not an observable event that we're going to be able to use to score you when you provide us information. So how can we handle these types of situations? And that'll be the focus of this talk. So let's try to briefly illustrate the problem with a bit of a joke example. We'd like to know the prevalence of cheating in a class. And so let's go through some attempts to solve this problem. First try here, we could simply ask, are you cheating in class? We could get some statistics on the percentage of cheaters, but you can see how this might go wrong. It turns out nobody cheats in classes. Okay, so perhaps we need to get money involved, incentivize participation, and you can see this will go very well for us as well. I'll pay you $1 to tell me whether or not you're cheating in class. Still nobody cheats in class. Perhaps we're not setting the incentives strongly enough. We can, offer $1,000. This is also going to go very well for us. So, okay, clearly we're missing something here. We have no way to tell if people are telling the truth. We don't have this ground truth. And, we could go in and actually try to verify a handful of people's answers, but let's assume we don't have that ability. So, or for now, actually, let's give ourselves a made-up technology. Let's imagine that we have the ability to verify whether people told us the truth in response to this question, but we can only apply this technology voluntarily on individuals. We have some way to check people. So let's say I have some magical procedure to determine whether or not you've cheated. You can agree to participate in this, and so I could go and ask people, well, how much would you like me to pay you to run it on you? And this is, of course, not going to go very well. Okay, so this could get expensive, but we know how to incentivize truthful bidding with truthful mechanisms. So maybe we can run a second price auction. So I have this magical procedure to determine if you're cheated. I'm going to run it on the k lowest bidders and pay each of them the next lowest bid. What's your bid? And now, finally, it gets interesting. Oh, $5, $1, we go through all the people in the class, and then somebody says, uh-oh. Now, in some sense, you may feel that I've solved the problem. There are a bunch of people who are perfectly willing to let me run this technology on them for just a handful of dollars, and then all of a sudden we get to somebody who flees the room. We didn't need to run the technology on him. We didn't need to pay him to start to be suspicious. But what I'm trying to do is highlight here that there are a couple of things that are giving us trouble in this setting. One of them is the lack of verifiability, which for the sake of illustrating the other problem, I tried to assume away. But then also there's this privacy issue. So the amount of money that I need to pay somebody in order to get at their data may be highly correlated with their data. There's some difficulties when we're trying to gather sensitive information. So I want to simultaneously think about how to deal with verifiability issues and privacy issues when our goal is to aggregate beliefs. So,
but it seems like a lot relies on you saying to them that you have this magical procedure and actually then believe in that. So
I'm not going to rely on any magical procedures later on in the talk. This is just to illustrate that even with magical procedures we have some difficulties. Okay. But let's try to do this without magical procedures. I agree with you. Okay, so we'd like to work on this problem of buying private data without verification, but that sounds hard. We identified two challenges, so let's take away the challenges, figure out how we might address the problem without these challenges, and then try to slowly put the challenges back into the problem and see if we can figure it out. So first I'm going to get rid of both of the hard parts of this problem. So buying data. So it's not private, we're not worried about privacy, we're not worried about this verification issue. So the data is not sensitive, and we have the ability to verify that you've given me your true information, or somehow at least to incentivize it by comparing it with some publicly observable outcome. And this is a really easily solvable problem. So let's try to make it a little bit more formal. What's the problem we're trying to solve here? We have a population of n individuals. Each of them has some hidden bit, we'll call bi for individual I, and our goal is just to estimate the average of these bits accurately while not paying people too much to do so. Any thoughts on how we might do this? If we have verification, we're not worried about privacy. I I just want to figure out what's the average value of the bits in this room, and I've got to somehow incentivize you to hand over your data. How might I do that? Any thoughts?
BCG?
Yeah, so run a second price auction. So we have some ability to, or I mean, if we have a publicly observable outcome, you can go with the prediction markets approach that we were describing before. There are technologies that solve this problem. This is the easy version of the problem. We want to do something much harder. So let's now focus on the problem of buying private data, but assume away the verification issue. So we have the ability to check whether the data you gave us was correct, or to ensure that you will never lie to us, but we still have to incentivize you to talk to us. Okay? Okay, so let's try to give ourselves a formal setting to study again. So here, the setting is going to be that each individual, again, has a hidden bit, BI, and we'll assume that individuals have privacy parameters, which you can think of as sort of a cost for having their data be used in our computation. Think of it as sort of how an individual experiences a loss of privacy. That's how we're going to denote that. And I should say that there's been a lot of work in the computer science sort of privacy community looking at these issues of how you can buy private data in settings where you have the ability to verify or where you don't have to worry about individuals lying. So a paper we've already heard about in talks earlier is this work of Ghosh and Roth, which introduced this problem of buying private data. And they show some very nice both positive and negative results in this space. So they give, as was mentioned, truthful auctions to get accurate statistics when individuals don't care about the privacy of their costs. So what do I mean by that? Well, if you're in a situation where there's no correlation between how much I have to pay you for your data and the data itself, the problem gets much easier. And I can basically use standard economic techniques in order to collect data from individuals. When there's potentially a correlation there are very, very strong impossibility results, actually. So we see the first results there in work of Ghosh and Roth and subsequent work of Nassim, Badan, and Shao, showing really that if you want to design individually rational mechanisms, when the costs themselves are embarrassing, so the fact that I need to pay you $1 million in order to participate in my survey already tells me a lot about the data you're about to give me, and if those payments are visible, then we have a serious problem. We really have some impossibility. So there's been a bunch of work in this space trying to respond to these impossibility results, and some of it has been sort of changing the assumptions, some of it's been changing the goal. So there's some nice work of Fleischer and Liu leveraging some additional information that you might have in order to give you power in this space. So if you assume that those CIs, the ways that people experience cost from privacy, are drawn from known priors, and you know those priors exactly, it turns out you can get around these impossibility results. I also have some work in this space that gives up to some extent on the guarantee of individual rationality and slightly revises the model of privacy costs that lets us get around some of these impossibility results. And there have been also some other positive results leveraging some natural assumptions, like maybe there's a monotonicity of the correlation between the bits and the costs, and some known bounds on how many players' costs exceed a particular threshold. You can leverage this type of information in order to say something positive in this space. Today I'm going to step away from these impossibility results through a different type of assumption, which is we're going to be in a Bayesian setting, which is in some ways similar to the Fleischer and Liu assumptions, but for them, if their Bayesian assumptions were wrong, then privacy went out the window. For us, if our Bayesian assumptions are wrong, we still get privacy, but correctness goes out the window, which to me is a much nicer way of doing things, because we really want our privacy to be strong universal guarantees. Accuracy is the place where I'm willing to give up if our assumptions are wrong. So what do I mean by a Bayesian setting? So we're going to assume that for individuals that bit cost pairs are drawn from some known joint distribution. So there can be a relationship between your private information and how much you are harmed by having your data used in the computation, but that relationship is understood. So you can think of it as maybe the bit is drawn first, and then there's some known conditional distribution over the costs, and then your cost is drawn from that conditional distribution. Okay? So we're going to assume that the agent's cost doesn't give her additional information about other agents beyond what was conveyed by her bit. Okay? And again, so this notion that there's a sort of distribution over bits, and then for each of the bits there's a conditional distribution over cost that satisfies this assumption. So that's maybe the easiest version of this model to carry in your head. So, sort of just as an example, we might be in a world where before you see your bit, you know that the prevalence of bit 1 is 50%. Once you see your own bit, that changes your beliefs about other people's bits. And so if it's positive, you might increase probability, negative, you might decrease probability. And then when we think about where these costs are coming in, so we might be in a world where there's some particular conditional distribution on costs given bit 0, and some other conditional distribution on costs given bit 1. And these distributions are going to be known, understood by everybody. So this is the Bayesian assumption that we're going to leverage, and like I said, our privacy results are not going to be conditioned on these Bayesian assumptions being correct, but if you're getting these Bayesian assumptions somewhat wrong, it's going to degrade the accuracy of the computations you're going to be able to do. And it's these general Bayesian assumptions are going to let us circumvent the fundamental impossibility results that I alluded to earlier.
So here bit is binary, so it's either revealing or not revealing, I guess, no?
So think of it as I'm going to ask you a question like, have you ever cheated in class? And there's a true bit. You've either cheated or you've not cheated.
Who's looking at this conditional probability of costs?
So everybody is aware of what this conditional, what these distributions are.
So this is common knowledge.
This is common knowledge, yeah. And we're going to leverage the common knowledge aspect of this in order to sort of formulate proper incentives later on in order to get people to reveal information. Okay. So I want to give some sort of privacy guarantee, but I haven't yet told you what I mean by privacy costs. We're going to need to do that. In order to talk about privacy costs, in some sense, we need to model privacy first. And the notion of privacy that we'll be working with today is inherited from differential privacy. Again, we've heard a bit about differential privacy already. We'll hear more about it later. But I'll spend a little bit of time, for those of you who are less familiar with the notion, developing it here. Please ask questions if you have them. So differential privacy is a notion that comes out of work of Denor, Nassim, Dwork, McSherry, and Smith. We talk about epsilon of parameterized differential privacy for a mechanism. So it's a property of mechanisms which map from database space to some outcome space. So we talk about differential privacy for a mechanism if for any two neighboring databases, D1 and D2, that differ in one person's information. So D1 is a particular database. D2 is that database with my information added to it. If we can say that for any set of outcomes of the mechanism that we might be interested in, that the probability that our mechanism maps the first database to that set of outcomes is almost exactly the same as the probability that the mechanism maps the database with my information, the neighboring database, to that set of outcomes. So for those of you who haven't seen this definition very many times, it takes a little while to sort of parse all the pieces here, so I'll spend a little bit of time here. So this is really a constraint talking about the distribution over outcomes that's induced by a mechanism that you run on a database. It's a property of the mechanism. It's a property of the mapping. It's not a property of a particular outcome. I can't say that the number 5 or a particular regression is differentially private. I can say that the procedure that generated it is differentially private. And what that means is that procedure that generated it is constrained so that it would have behaved in almost the same fashion had I had a slightly different input database. So it's a sort of robustness or stability property of a computation that says that that computation is going to produce almost the same results even if the input data were slightly shifted. So if you're looking at the formal definition and trying to sort of make sense of this e to the epsilon multiplier, just think of that as a small multiplier. I think of it as a 1 plus epsilon is maybe easier to think about. If you're looking at this and saying, this is very odd, it looks like an asymmetric definition because I put D1 on the left-hand side and D2 on the right-hand side. I'll reassure you that I'm talking about any two neighboring databases, D1 and D2, and therefore I'm also talking about D2 and D1. Other questions, concerns about the definition going forward? Yeah, familiar.
I think many people
You've seen many of you have seen it many times in many contexts. So good. So just for intuition, if differential privacy is a guarantee that a particular mechanism enjoys, then that constrains the behavior of the mechanism so that if it induces a particular distribution over outcomes given a particular database, then it's going to be constrained to induce a similar distribution giving a neighboring database. And there are these useful interpretations so that if an individual is concerned about particular outcomes of the mechanism, she's guaranteed that those bad outcomes would have occurred with almost the same probability had she withheld her data from the mechanism or had she lied about her data. And this is where we start to get the ability to talk about incentives when we think about differential privacy. This idea that there's some sort of limited ability that individuals have to affect the outcome. So I've emphasized already that it's nice because it's a property of the mechanism behavior, which lets us step away from the issues of trying to model an adversary or talk about outside information that an adversary might have access to. And so it's a guarantee that stands regardless of the data that an adversary has or may have in the future, regardless of what an adversary might choose to do or her computational power. And there's some nice sort of composition properties that say if you do something that's differentially private and do something else subsequently that's differentially private, we can talk about the privacy guarantee of those two composed computations, even if they were chosen adaptively. And this also is a notion that allows for arbitrary post-processing. So if you do something that's differentially private, anything that anyone subsequently does to that computation remains differentially private. We don't have to worry about somebody coming up with a cool hack someday in the future that destroys the differential privacy guarantees that you have. So just since it's familiar to many folks here, to go quickly through techniques that provide differential privacy. So we're doing very, very simple computations, so we need only really the simplest techniques for providing differential privacy. There are more complex things you might like to do with data, where there are more complex and interesting techniques available, but if what you want to do is compute what fraction of a database has a particular property or some other situation where your output is just a single number, then all you need to do in order to preserve differential privacy is add some noise. And so you can ask the question, well, what should the shape of that noise be? How much noise should it be? And it turns out that the important parameter governing sort of how much noise to add is the sensitivity of the function that you're computing on the data set. And what do I mean by sensitivity? It's just a measure of how much one person changing their data or entering the data set could affect the outcome of that computation. And so, for example, if you're doing a computation that's just counting the number of rows in your database that satisfy a particular predicate or condition, then the sensitivity is 1. And it turns out if you add noise of a particular form that's scaled with the sensitivity of the computation of interest, then you enjoy differential privacy. And so what's this definition of the sort of the useful form of the noise. Well, it's scaled symmetric noise Laplace distribution. So just think of it as nicely concentrated noise, or if you're not familiar with the Laplace distribution, think of a Gaussian. It gives you a slightly different guarantee, but it's good enough. And so sort of the scale of the noise that you add is going to affect the level of privacy that you enjoy. So just to run a couple of examples quickly. So if you want to do a single counting query, for example, how many people in the database satisfy a particular predicate? Like I mentioned before, the sensitivity is 1. And so we can add noise that looks like Laplace of 1 over epsilon, where epsilon is the privacy guarantee that we want to give. Okay, so we talked about privacy. Now we want to talk about privacy costs. And as we saw in the previous talk, there is no one universally accepted way to model and think about privacy costs. I think there never will be. I agree with Alessandro. I think there are many things that are actually quite unsatisfying with the techniques that we have thus far. But nonetheless, let's go ahead and adopt a model. So for most of our results, what we do is adopt a model that was proposed in work of Nassim, Orlandi, and Smordinsky, which assumes that privacy costs can be arbitrary, but they're upper bounded by some linear function of epsilon. So if I'm subjecting you to an epsilon differentially private computation, the harm that you incur is upper bounded by some linear function of epsilon. So this is, I think, as these types of assumptions go, a relatively reasonable and benign assumption. Why linear? Honestly, I don't really know, but it's a start. So then what they do and what we do is adopt a utility model. So sort of the harm that you incur is bounded by this Ci times epsilon, and then you get a payment of some p. And so now we have some bound on your utility that you experience. We're not doing it here, but you could also potentially incorporate individuals having explicit preferences for manipulating the outcome of a computation. So remember, we're in this world where each individual has a bit. What we want to understand or do here is understand the prevalence of ones in the room. It's possible that you actually have some vested interest in me finding that there are lots of cheaters in the room or a few cheaters in the room, and so we might need to incorporate that into your incentives. We won't do it in this talk, but it's possible to talk about doing that.
Can I ask a more basic question?
Absolutely, yes.
So since you mentioned second price auction, and they're known to be very vulnerable to collusion.
Yeah.
And I might be much more comfortable colluding with them. If I'm a cheater, I might be much more comfortable revealing them a cheater to another cheater and colluding with the cheater on the answers than doing it to the designer. So my privacy costs could be different, but it's related just to some other participants with whom I might collude, or to the to the designer. So I'm not sure.
Yeah, so that's a really interesting issue. So this is not an issue that we're explicitly treating in this work. In this work, we are thinking about everyone interacting directly with sort of a central authority who's going to perform this computation and is going to publish the results. And when we talk about privacy, for the purposes of this talk, let's assume that you trust the central authority with your data and you trust that they're going to do the computation they promised to do, and what you're worried about is the final published result. You actually don't need to trust the central authority. You can introduce your own privacy by perturbing your answer locally, and a little bit further, once we have a mechanism, I can sort of point out where that would happen if individuals were going to provide their own privacy rather than trusting the central authority. So we don't get into that question of maybe having different privacy preferences regarding different people. I'm actually doing some work right now that I think is the first work in the differential privacy framework that tries to address that. And it turns out it can actually be really useful to take that into account. So we've been looking at various models of how individuals might trust different people in different ways. So maybe I trust you with my data more than I trust someone I know less. Maybe I trust you to perform the computation you've promised to, but I don't trust somebody else to perform the computation they promised to. And it turns out these sort of intermediate trust models where there's not one central authority, but also it's not a totally untrusted world where you feel you have to provide your own privacy, do interpolate in some sense between those two extreme models and potentially give you some interesting results in between. So it's a good question. It's a good thing, I think, an interesting thing to explore. I'm not going to do it here, but I will point out especially if you remind me once we get to the mechanisms, as sort of what we can do if people don't trust the central authority. Yeah, question?
I was going to suggest a sort of follow-up to that. So
yeah.
If you don't want to trust the central authority, one thing you could do is, given you've got no validation, you could ask each of the users to toss a coin, right, themselves. And if it comes up heads and they're not a cheater, then they report it, or tails, they report it. If they are a cheater, regardless of what the coin does, you always say heads. So at an individual level, when you give your report, you're not revealing with certainty that you're a cheater or not. But in aggregate, you still get a statistical shift.
So this is exactly what I wanted to say. What we, at least in the literature I'm familiar with, refer to as the randomized response mechanism. And so this is Warner 65 is the citation I know for this. So this actually provably provides differential privacy. And it's actually a fairly simple computation to do. If you guys haven't seen it, we can do that at the end if you're interested. So this is a differentially private mechanism, a great example of one, and it's one where you provide your own privacy, so you don't need to trust the central authority. And that's exactly what you could plug in to sort of our future discussion of mechanisms if you don't want to have that trust. Yeah, other questions at this point? Yeah?
Very simple one. This CI, is this observable, or is this a personal parameter?
Good. So we're going to assume so remember I talked about those distributions. So we're going to assume that the distribution over BIs and the conditional distribution on CIs is known, but I, as the central authority, cannot observe your BI or your CI. So I have some understanding of how they're distributed and how they're correlated, but I don't know your particular value.
You know the exact distributions then?
We're going to assume we know those exact conditional distributions. And if our understanding of the conditional distributions are flawed, then that will harm our accuracy to some extent. Yeah. Other questions? Okay. So just to mention in passing, this is an old slide, so it only goes up to 2012. There's been a lot of interest in privacy and mechanism design. Just to give a sample of things, if sort of these types of questions are interesting to you and you want to get a view into what's been going on in the differential privacy literature in particular, come talk to me. I'm happy to give you pointers into the aspects of the literature that might be most relevant to you. But I just wanted to say there's a lot that's been going on in this space that I'm not talking about here. Okay, so let's get back to our question and remind ourselves of this setting that we were trying to address. So now we have some notion of privacy, we have some notion of privacy costs. What were we trying to do? So we're in this world where everybody has a bit, everybody has a privacy cost. The distribution over bits, just to keep things simple, the distribution is publicly known. Given that you have a bit of 1, the conditional distribution of CIs is publicly known. Given that you have a bit of 0, the conditional distribution of CIs is publicly known. And so we're in this situation right now where people have privacy concerns, but we don't have to worry about verification. So we're going to assume that if people reveal something to us, that they're revealing truthfully. Okay? So intuitively what we'd like to do here is, for each of these distributions, we'd like to find the value of theta that gets us some 1 minus epsilon over 2 fraction of people to participate, and we'd like to pay people accordingly. Does that make sense? We just want to get enough people in both of these distributions participating that we're going to have a pretty good estimate of the prevalence of the bits. So we just have to figure out how to set people's incentives so that enough people are willing to pay. Because for us, we don't have a verification problem right now. We'll get the verification aspect back in a few minutes. That make sense? So this sort of warm-up mechanism that you might come up with is from each individual, you're going to collect a reported bit. They can give you a 0, they can give you a 1, or they can give you a, forget it, I'm not talking to you. And then you're going to release, so the count of ones that you got, plus some noise, that's what that lambda is representing. Don't worry too much about what's going on inside the lambda for the moment. So you're going to release the average value there. You're going to pay people this 2 theta over epsilon n. This is going to be some level of differentially private that's inherited from the amount of noise that we added to people's values. Again, don't worry about what's in there for the moment. And we're going to get error from 2 sources. So we're going to get error because we added noise to our estimate of the prevalence of the bit, and we're going to get error from non-participation, because there's some people who we were just not paying enough in order to incentivize them to participate, and so they said, forget it. Okay? And so you can, from this, calculate the cost of running this mechanism. So this is really just following this basic idea that once we figure out how much we need to pay in order to get most people participating, then we can add sort of the corresponding right amount of noise to their answers in order to compensate, to have the sort of compensation match the privacy loss. And then we have a mechanism that's pretty simple that solves our problem. Okay, so this is for the version where we care about privacy, but we didn't have a verification problem. Sounds good?
Quick question.
Yeah.
So the expected error that comes from noise, I understand that, and so less than epsilon over 2 that comes from non-participation. Is that non-participation just sampling error, or does it account for selection bias associated with the correlation between the costs and the bits?
Good. So there is going to be some epsilon fraction of people who simply don't participate, and we're going to make no assumptions about which party they came from, the ones or the zeros. We're just going to say we got them wrong. So it accounts for that sample sort of bias that you would get, because maybe the threshold that you needed for a participation among zeros is very different from the threshold for participation needed among ones.
Right, so if everybody who didn't participate was a 1, then I'm going to have a biased estimate of the share of people.
But this epsilon controls the amount of that bias. Yeah, it's a good question. Okay, so now let's do the other easier version of the problem. So let's cross out the privacy and focus on the question of how to incentivize truth telling. Okay, so what do I mean by this? So we want to be in the prediction markets kind of a world where everybody has a bit. It's no longer a private bit. You don't have some sort of burning desire to hide it from me. You just want to be incentivized properly to hand it over. But now the difference from the prediction market setting is that there's no election that's going to happen on a particular day that we can use to incentivize you to tell us what you think. There's no way I can check that you're really telling me what you believe. There's no way that I can sort of check that you're sort of incentivized to provide your best beliefs using some sort of verifiable or ground truth. So again, we're going to use the idea of sort of Bayesian assumptions. So there's some publicly known prior under which other bits are conditionally independent of your CI given your BI. And so we're going to assume that the bits are informative and positively correlated. And now there's some really nice literature that addresses this problem. It gets known as pure prediction. The first paper in this line that I'm aware of is Miller, Resnick, and Zeckhauer of 2005. And the key idea here is to reward participants for giving reports that are good predictions of other people's reports. Because we're assuming that we have an understanding of these underlying distributions, and that there's some correlation between your data and someone else's, now I can potentially incentivize you to tell me what you think by paying you for how well you predict what other people say they think. Okay? So recall our sort of example Bayesian setting. So we'll assume that the mechanism, like the players, knows the probability that others have 0, given that you saw 0, and the probability that others have 1, given that you saw 1. So this is, again, common knowledge. And so now we want to come up with a function of an individual's claim and a random other person's claim whose expectation is maximized by truth-telling, assuming the other person also truth-tells. So we're going to look for an equilibrium type mechanism such that if I randomly paired two people up and asked them their beliefs, they would be incentivized by our mechanism to truthfully report. And I'm going to do this because I have this understanding of what a 1 for you predicts about a 1 for you. And so the idea that does this is a proper scoring rule. And so basically this is a way of incentivizing participants to truthfully report their beliefs. One example that maybe you've encountered if you've seen scoring rules before is the Breyer scoring rule, but maybe it's not so useful to go through the particulars of a scoring rule, but just to say that a scoring rule is a function that has this nice property. It tells you how much to pay for each report, given that you understand how to interpret that report as a prediction of somebody else's report. So I understand that when you say, I got bit 1, that means that you believe that another person in the room got 1 with probability 0.65. And therefore, I can set a function to how to pay you for that report that maximizes your payoff for saying 1 versus for saying anything else. So maybe let's not worry about the particulars of any particular proper scoring rule, but there are many ways to design these. They get used in lots of interesting settings. We can talk about them more later if you're interested. The big thing here, though, is that it results in truth-telling as a Bayes-Nash equilibrium. So this is basically a payoff function that lets us use these Bayesian assumptions in order to get people to tell us what they really think. Okay? And so this solves the current version of the problem that we're trying to address, which just says, okay, our new mechanism is we're going to randomly pair people in the room, and we're going to pay person I based on how well his report can be interpreted as a prediction of what person J reports. We use a scoring rule to do that, and this is pure prediction. Okay? Questions about the sort of core idea there? That looks like the beginning of a question. It was a big sigh.
It's very familiar, but I can't quite pin down if it resembles me.
I'd be interested if it resembles something else in the literature, because I haven't.
Maybe
Somewhat like the Kramer-McLean idea.
What?
The Kramer-McLean idea, right? So, as an option. Okay, maybe I'm.
Well, feel free to elaborate if.
No. So
I think that would be helpful.
The surplus.
Sorry, of extraction of surplus. Yes, that might be why you're finding it familiar.
Yeah. Might be, yeah.
So.
Do you want to elaborate if that might help people?
So there's this idea when you have two correlated bits, the idea that I can get, so there's an idea in auctions that I can get full extraction of surplus by getting these people to bet against each other.
Yeah.
This paper is basically cleverly using scoring rules to elicit that correlation similarly, but the idea goes further back, and for auction people, a different set of Pavlovian responses.
Okay, yeah, that's
Here,
helpful.
similar terms.
Yeah, but in some sense it's not surprising that as a proxy for verifiable information or for an observable outcome that we could leverage correlations between people's data. It's another thing that could be used as a check, and this is just a clever way to really get that check right. Okay? Other questions at this point? So we solved 3 versions of the problem. Now let's try to solve the version that we set out to solve, which is this original title, Buying Private Data Without Verification. Okay, so now we've got both the challenges of privacy and the challenges of verification to deal with. Well, let's combine some of the ideas that we've developed so far. Why can't we do this peer prediction thing that we just did on the previous slide in the context where we care about privacy? So there are a few issues that come up when we start to care about privacy. So the first one is that each individual's payment in this mechanism reveals too much about her. Because we're paying people basically for how well their bit predicts somebody else's bit. But that payment tells us a lot about what they stated their bit was. Another problem is that each individual in this mechanism is being paid based on a single other player's bit. So when I find out my payment, I learn what somebody else's bit was. And this is problematic for differential privacy. Another challenge for privacy is that, well, under privacy, we're not going to assume that there's some bounded costs that individuals experience for privacy. We'd like to be able to assume that there are some people who value privacy so much that we're just never going to get them in the door. They're never going to participate in our experiment. We'd like to understand that, okay, there's going to be some loss in accuracy because of this, but we'd like to be able to control that somehow. But unfortunately, the existing mechanism potentially runs into some problems when you don't have full participation. And in particular, one of the issues that comes out sort of not just from full participation, but also because we're directly introducing noise for privacy purposes, we're going to necessarily need to, is that somehow the incentive to truth tell has to be robust to this noise. So we need to somehow not destroy our equilibrium, because we needed this Bayes-Nash equilibrium property of our payment function, and we need to somehow be robust to the fact that some people aren't going to participate. We're going to introduce some noise into our computation and figure out how to get that robustness in there. And we have some interesting feeling tension going on here. So as you introduce more noise, that directly harms your accuracy, of course, but it also encourages participation, which helps accuracy. So there's going to be some interesting balance that we want to explore there. Okay, so we've got a bunch of things that seem like they go wrong when we want to deploy this peer prediction mechanism in a privacy context. So let's talk about how we're going to deal with each of these. So the first one is this issue that the amount you're paid is too revealing. And in some sense, we're going to assume this problem away. We're going to talk about a slightly different privacy guarantee than the differential privacy guarantee I gave you before. This one's known as joint differential privacy. And the idea there is that we don't need to publish the payments of each of the individuals. Each individual can receive their payment separately. And what we want to guarantee is that even if all the other people in the room colluded and showed each other their payments and showed each other their bits, that still you are going to have a guarantee of differential privacy. So it's a slightly weaker guarantee because the other people don't get to see your payment, but other than that, it's the same guarantee we had before. Seems pretty reasonable. Okay, so now we want to try to do a private version of the peer prediction mechanism. So we're going to take advantage of some things, some sort of properties of the Breyer scoring rule, which is this particular proper scoring rule that I mentioned before. So I'm just going to ask you to sort of take it on faith that there's some things that we can do to scoring rules that maintain some of their nice properties. We can talk a little bit more about that in detail if you guys are interested. So here's the basic mechanism. It looks a little crazy when I first put it up there, but it's actually very, very similar to what I showed you before. So basically, we're going to ask each people to provide us with a bit, a reported bit. It's going to be a 0, 1, or a forget it, I'm out of here. I'm going to compute the prevalence of ones in these reported bits. I'm going to add some noise to it. That's that lambda on line 2. Again, don't worry so much about that thing that goes inside the lambda. But importantly now, I'm going to compute a bunch of different things. So I'm going to compute the overall prevalence, so that B bar over N, in the population of reported ones. But I'm going to also compute the prevalence of reported ones in each size n minus 1 population, so leaving each person out. I'm going to release the A bar, so the overall reported prevalence of ones in the population with some noise added to it. But how I'm going to pay people is going to depend not on the A bar, but on their particular sort of A minus 1, so excluding them, A bar. Maybe for a moment, let's skip where the payments are coming from, and then we can come back to that. So the rest of the reasoning is going to be fairly similar to what we saw before. We're going to have to do some work in order to get it to be an equilibrium for agents to truth tell, so we'll talk a little bit more about why we haven't destroyed our equilibrium properties. But when we talk about error, sort of given that you believe that I've created this equilibrium where people will truth tell, error is the same sort of reasoning. We're going to get some of our error from the noise that we directly added, some from non-participation. We have a similar idea of picking out thetas in order to get high enough participation. And then we're going to suffer some costs. These gammas that are showing up in here are coming from sort of posterior values, sort of our understanding of how somebody's posteriors form given a bit that they see. And then we need to do some reasoning about privacy for this mechanism. So the things that are missing here are sort of reasoning about the equilibrium and reasoning about privacy. And privacy actually is really, really easy, which is one of the nice things here. And why do I say that? Well, because I mentioned before that differential privacy has these nice composition properties. So if you do something that's differentially private, then you do something else that's differentially private, sort of privacy guarantees add up. So basically, in order for simple mechanisms, in order to figure out where the privacy is, you just need to look at what's being made public. So in order to do joint differential privacy, you need to sort of fix an individual and look at the information that's available to everybody besides him. And so we really just need to look at sort of we've got some publicly released A bar, so we need to look at the privacy properties there. And then fixing an individual I, we need to look at the privacy properties of the payments of all of the other individuals. And so we actually have sort of a relatively easy privacy analysis to do. So I'll do some quick sketches of proofs here. You can ask me questions. Yeah?
So it seems like, if you just look at the payments, so their payments, all payments will be maximized collectively if they all report like they're cheaters, right? But should I think about it that these kind of payments are not enough to compensate the costs they actually incur from the
So this is an excellent point that I was hoping to get to a bit later on. Peer prediction mechanisms have a huge downfall, which is multiplicity of equilibria, including equilibria where everybody misreports 0, everybody misreports 1, and it turns out there are 9 equilibria of peer prediction mechanisms.
But I think this is how we can think about collusion in this case, right?
Yeah.
They just collude. Right?
So yeah, so it's a different kind of collusion than sort of privacy-related collusion. I actually have a different paper on peer prediction, which I'm not going to talk about today, where we analyze all of the equilibria of the peer prediction mechanism and show that it's possible to take a peer prediction mechanism and change it into one where truth-telling becomes the focal highest payoff equilibrium. So we didn't do that transformation on this, but there's sort of a transformation you can do on any of these types of mechanisms to solve that problem of the existence of these other equilibria. So it's a really good point. It's a solvable problem, but it's not one that we're addressing right here. Yeah. Okay. So what's a sketch of I'll do this quickly, the sketch of how you argue accuracy. Well, accuracy is going to come from truthfulness of enough players. We show the existence in this new mechanism of a threshold strategy equilibrium where all agents with costs below a particular threshold are incentivized to truth tell. And then we find a threshold such that a large fraction of players have costs below it, and for all players conditioning on having either bit, the posterior says a large fraction of others have costs below it, which is how we start to be able to sort of redo our equilibrium reasoning that we were doing before. Let me maybe skip through some of these things because I wanted to have a little bit of time for questions and I wanted to say a few other things. If you'd like to get back into some of the details there, we can go back and talk about some of them. But I wanted to mention that there are some things that are a bit unsatisfying about this approach that I think are worth thinking about. So one is this prior. It's in some sense a very, very strong assumption that we're making, that there's some known distribution on the prevalence of the bit, of the conditional distributions of C's given the bits. And it would be nice to relax this assumption. In the non-private peer prediction literature, this actually has been done. The sort of key word to use if you want to Google search this is Bayesian truth serum. It's not quite clear how to do an adaptation of that approach in the privacy-aware context, but I think it's possible. There's this issue of multiplicity of equilibria that we were just talking about, which, as I hinted, is in some sense mostly solved, but I think there's still some really interesting work to do there, and in particular, when we do this analysis of all of the equilibria of peer prediction and show this technique for modifying a mechanism in order to make truth-telling focal, we do a very, very simple version of the problem, and it's still an incredible amount of work. And yet there's, I think, a very intuitive reason that this should work. It shouldn't be 60 pages of math. And so I think we're really missing something here. And so I think it's worth revisiting this question and trying to come up with simpler techniques for addressing it that might let us solve more general problems. And then I wanted to mention briefly, since I'm here, so as I hinted before, we were doing a really, really simple computation today. We just wanted to understand the prevalence of an embarrassing bit in a population. But in reality, anybody who works with data these days, if it's coming from humans, is dealing with this problem that they're doing a computation. If the data is potentially sensitive or there's some issues in selection that might result from sensitivity, they're dealing with the fact that they may not be getting sort of the truth. And so you can think about this question of how do you incentivize people to report data for other more complex types of calculations. So in particular, we have a subsequent paper looking at the problem of you want to do a linear regression, but the data on which you're doing your regression is elicited from individuals who may have privacy concerns. And so we look at using similar ideas to the ones here for sort of more complex computations. In the case of linear regression, part of why it becomes interesting is because the standard differentially private estimators for linear regression are no longer unbiased, and that introduces some sort of interesting problems for us. But I think this sort of general problem of take a computation of interest and think about how you incentivize people to report data to you for you to do that computation is an interesting one in the context of privacy and where you don't have these verifiability types of tools to deploy. But more generally, I've done a bunch of work in privacy preserving synthetic data, sort of thinking about privacy for more complex objects than just numbers, thinking about connections between privacy and statistics, how one should be doing science on large data sets, fundamental trade-offs in the space of differential privacy and accuracy, markets for private information, including some things related to what Alessandro has mentioned. And also, just so you know, I'm not an economist, but sometimes I pretend to be one. So I'm also interested in a number of issues in game theory, dynamics in games, networks in games. So in case you share an interest there, I just wanted to mention. And thanks all.
questions
Yeah.
we went, but maybe there are like another question.
Coffee break.
I have like,
Oh, yeah.
I can ask it, but
Yeah, yeah.
no, it just seems like all these settings like private cost. But again, I come from the auction literature where we have private values and common values. How would I think about something like common values in the privacy context when my utility depends on the privacy settings of other people? Or I mean,
So you're looking for sort of an analogy to the
Yeah,
auction
exactly.
setting. Yeah, so sort of a common value analogy.
I mean,
I think
something
maybe
like
the closest thing is just to say that because of the technologies that we have and the ways that we deploy them, in many situations, the best thing that we know how to do is basically to give everybody the same privacy guarantees. It's not the same issue, though.
understand.
Yeah,
I
it's
was hoping.
I don't have a good answer. If somebody else has a good analogy to draw
Well, I'm
there,
not sure
I
it's
would.
a question. I was
Yeah,
hoping.
yeah. Unfortunately, I don't think I have a good answer there. But if somebody else does, I'd like to hear it.
Okay, so let's take a break and reconvene at 4 o'clock.
Makes sense.